Sometimes the biggest revolutions start with the smallest mysteries. Today, we're diving into one of those, a chemical puzzle that could hold the key to a clean energy future. We're going to crack a chemical code.
And it all really boils down to this one huge question. We all know hydrogen is this amazing, super clean fuel, but it comes with a massive storage problem. And solving that is one of the biggest challenges in chemistry today.
Think about it. You can't just pump hydrogen into a regular gas tank. It's the lightest element in the entire universe. So trying to pack enough of it into a car to go a decent distance, well, that's the hurdle we've got to get over. So let's just frame this challenge, right? For years, scientists have been on the hunt for a really clever way to pack those hydrogen atoms super tight so we can carry them around and use them whenever we need them. And that leads us to this absolutely brilliant idea. Instead of dealing with high-pressure gas tanks or super cold liquid hydrogen, what if you could just lock it all away inside a solid, something you could just hold in your hand at room temperature, kind of like a chemical sponge that just soaks up hydrogen. So you're probably wondering, what is this chemical sponge made of? Well, let's meet the main characters in our little chemical drama. Say hello to ammonia borane, or AB for short. This stuff is amazing. It's just a white powder, it's lightweight, it's safe, and it is absolutely stuffed with hydrogen atoms. Seriously, a great way to think about it is like a battery, but instead of holding electricity, it's holding pure, clean hydrogen fuel. Okay, but there's a catch, right? There's always a catch. You've got all this hydrogen locked up tight inside this solid. How in the world do you get it out when you actually need it? Drive your car. You can't just squeeze the sponge. You need a special key. And this is our key. This incredible molecule, researchers just call it CAT, is a catalyst. It's basically a tiny molecular machine, and its whole job is to grab onto that ammonia borane and pop the hydrogen right out, over and over and over again. But here's the thing about CAT. It worked almost too well in the lab. And for years, scientists couldn't quite figure out why. It was hiding a secret. And this is where our mystery really kicks off. When you ran the experiments, CAT was just a total rock star. But when scientists tried to model the reaction on a computer, the numbers just didn't line up. Theory and reality were telling two different stories. And that's a huge red flag when you're trying to really understand how something works. To really get it, you gotta see CAT as this complex little machine with a bunch of different parts. Scientists knew the action was happening at one of these active sites, but they had to figure out which part was the real engine, doing all the heavy lifting. And here it is. This was the critical clue. In the lab, scientists could see that the catalyst's arms, they're called ligands, were actually moving and changing during the reaction. But the computer models, they were treating those arms like they were totally rigid and frozen in place. That was the mismatch. So how'd they finally crack the code? Well, it meant they had to build a brand new tool for the job. The big breakthrough came from a team of researchers who decided to build a better model from the ground up. They created a new simulation where the catalyst arms were flexible. They could react, they could change, they could do everything they were seeing in the real world. And bam, the new model finally captured what was really going on. It revealed something that no one had seen before. The catalyst actually uses a little bit of the hydrogen to power itself up before it starts releasing the rest of the hydrogen as fuel. So here's how it actually goes down, in 4 simple steps. First, the catalyst's arms grab some hydrogen to power up. Then, this newly energized catalyst snags a fresh molecule of ammonia borane. Step 3, it quickly and super efficiently releases hydrogen gas. And finally, it resets itself, totally ready to do the whole cycle again. The mystery was finally solved. But you know how it is in science. Solving one mystery often leads you to an even bigger discovery. They didn't just figure out how it works, they figured out how to make it work best. See, this new model was so good, it could do more than just explain what happened. It could predict what would happen. And it showed that how much the catalyst's arms were powered up directly changed how fast it could work. And that led them straight to this, a sweet spot. It's kind of like a Goldilocks situation. Turns out, the catalyst isn't at its best when it's totally clean, and it's not at its best when it's fully powered up either. The absolute peak performance happens right in the middle, at a very specific level of power-up. And they could even put a precise number on it. At that sweet spot, the energy needed to kick off the reaction drops to its absolute lowest point.
just 25.4 kilocalories per mole. In the world of chemistry, that's like finding the smoothest, fastest, most perfect downhill path for a reaction to take. It's maximum efficiency.
So, let's step back. Why does all this matter? Why does cracking one tiny chemical code get us so excited? Well, it's all about what we can do now.
Because once you truly understand how a machine works, you can start to improve it. Now that chemists have the exact blueprint for this little molecular engine, they can start tweaking the design, building new catalysts that could be even faster, more durable, and maybe even cheaper.
And really, that's the whole point of this kind of research, isn't it? You have to painstakingly figure out the how before you can even dream about the what if. This work gives future scientists a powerful new playbook for designing the next generation of catalysts. And that kind of leaves us with this big, exciting question. Of course, it's a long, long road from one scientific paper to a whole world running on clean hydrogen. But sometimes all it takes is finding that one perfect key to unlock a very, very important door.